All right, if you're looking at this video, you are trying to identify which equations go with each of these graphs. Now, remembering that for each of these, it is a multiple choice scenario, but the main thing we're doing is looking at a graph and understanding what possibilities it might have. For example, when we look at number one, we see that we have a continuous function with no asymptotes. So out of our six trigonometric functions, the two that must apply are sine and cosine, which you are currently already seeing as your multiple choice options. Now, on these, there are some things to consider. For the first six questions on this assignment, there is no shifting to the left or to the right, nor up nor down. So we are just looking at graphs where they would originally be, just maybe the period has changed or the amplitude has changed. So when we look at each of these graphs, one thing to consider is where's the midline? So every graph out there has a midline. We see in number one, for example, we have the middle of the graph being shown at the x-axis. And with sine and cosine, there's a high and a low point that they reach, which we signify with the amplitude. So we have that here and here. And so then we can start talking about how far of a stretch has this graph gone. So for this particular graph, the distance from the midline to the top is 5 units, and the same would go for the midline to the bottom. Something else to consider is how long does it take for the trigonometric function to complete a cycle? So for number one here, we see that it is a wave. It continues on and on. But for one cycle to complete, if we started here, for example, we see that once we reach this point, the graph is going to start repeating itself. So something we consider is how long was that period? And for this one, if we started the cycle at 0 and ended at pi, that would be a total length of pi units. So the period is pi. Okay, so we have a amplitude of 5. We're trying to think of how does this period help us with the equation. Well, the period is determined by the coefficient of your angle. We give that the label b in our equations. So what we have to recognize is this is either sine or cosine, and the period of those functions is typically 2 pi. So what has happened to change this period to being pi? And so there's this idea we can use. If we know the original period of a function, and we know that b has the opportunity to change that period, the ability to change that period, then we can solve for b comparing the original period to what it currently is in our situation. For example, in graph number one, the period of the function shown is pi. But for all sine and cosine functions, the original period is 2 pi. So we are asking ourselves what value of b is going to do that for us. And so solving this equation using some algebraic steps, we can multiply by b on both sides, and we get b times pi is equal to 2 pi. And if we divide by pi on each side here, we end up getting that b is equal to 2. So now that we have those two values, that a is equal to 5 and b is equal to 2, we look at the cycle of this graph. Since the graph has not shifted left or right or up and down, we can look here and say which of the two functions is going to start at the amplitude on the y-axis. And out of the two graphs we have seen, cosine is the one that starts at the top of the graph here. And so we deduce this is cosine. And so for this particular graph, we have y equals 5 cosine of 2x. And we can use the same strategy for a variety of scenarios. For example, we look at number 3, and we can see the shape of this one is either cosecant or secant. Now, as far as determining values that we saw in the last one, we still reason through the same things. Is there a midline to this graph? Is there a divider to this graph? And you can see one, again, it's right at the x-axis, to where this is going through the middle of the graph, to where the upward opening parts of the graph are the same distance away from that midline as the lower parts of this graph. And using that same idea, we can identify an. And so we can see that getting from this midline to each of these graphs is equally spaced, showing another one here. The distance from the midline to either part of our graph is the same, and I'm going to zoom in just. And once we have that visualization, we can start talking about how far is it from the midline to either part of our graph. So very similar to what we did with sine and cosine. How far is it from the midline to that turning point? And in this case, that spacing right here is pretty small. It's only a half unit. And so I recognize right away the leading coefficient on these graphs must be 1/2. So now that we have that, we talk about what is the period of this graph. So remember, a period is the length of a graph before for it to complete one full cycle before it starts repeating. And so this graph alternates between an upward opening and a downward opening portion. So the question is, how long does it take before we have another upward opening part of this graph? And so if we start at 0 here and go all the way over, we see that after this part of the graph has ended, we're going to have another part that opens up again. We're going to start repeating. So that spacing here from 0 to the end is 2 pi. And so we know the period of this function is 2 pi. And then we start asking ourselves, is that different from what the graph of secant or cosecant would be? Well, because secant and cosecant are based off of sine and cosine, they actually have the same period as sine and cosine. So since the period has not changed, we do recognize that b is going to equal 1 on these. So then the last question we ask ourselves is, if our graph is undefined at the y-axis and we have not shifted to the left or the right, would this be a secant function or a cosecant function? And the graph that is undefined at the y-axis initially without any shifting is based off of sine. So that is our cosecant function. Because wherever sine is equal to 0, its reciprocal cosecant is going to be undefined. And because of that, we now know that we have a cosecant function with an a value of 1/2 and no change to the period. So we have y equals 1/2 cosecant of x, which again, the b value is 1. So we could have 1x there, but the 1 is unneeded. And so we'll leave it as such. And this same idea can be done with any sine and cosine, secant and cosecant function using these spacings without any shifts. In the next video, we'll talk about using a similar method for tangent and cotangent.